just in general, everything.
Okay.
Everything based on the same, exactly the same. And yeah, somehow it's not really. It said that it was here on this function that I just changed from arc to angle, but when I run it, it looks like this.
It looks
Can you
like
see?
zeros, huh? So that probably means that the problem is in HRC calculation, 15 lines somewhere.
Here?
Somewhere here it has to be, because otherwise, or time, but time is correctly specified. I can see that already. So it has to be. It has to be. So let's check it. Yes. So sinc t divided by t symbol cosine p beta t symbol divided by, then there is the difference, double beta. But it does look correct. So
Yes, that's the thing that like I thought it was with my parameters that it might not be correct, but then I tried with the ones you were trying, and it was showing this kind of mistake, and I made sure that the coding was the same.
but
And
maybe you can send me this file so I can launch it and see if it works in Octave the same.
just a second, where can I send it? Is there any? Wait,
Yes, you can send it in Teams just by drag and dropping it in chat.
where is the chat? Can't find the chat part. Can you type something so I can find it easier, please?
Yes, a minute.
Or maybe I can't while sharing. No, it's not that.
Yes, I can show and share. So once you open Teams, this active call, yes, you can press it here, conversations, and accordingly you can send files here as well. Here attachment, yes. So you can send this file and I will open it in Octave and try and launch it to see if it gives the same result.
I am trying. I just don't have that button, I think, because sorry. Look how. Can you see my?
Yes.
I don't have it here. That's why I'm trying to. Maybe it's here actually.
I think it is in that multiple, where that's multiple dot after the button with raised hand.
If he is not a member in the group, in the teams, he will have no tab for the chat.
Because of this guest status.
Probably could be because I joined from Ortus.
But you can send me then by email. Not a problem. You can send me from email.
And just send it by email now.
Yes, please.
Okay, just send to you.
See, yes, I have received the script. So I'm going to copy it. I need to share my screen now and make a new file with wait a minute, where did it go? Here is your code. So I'm going to save it as test code and let's launch it. I see. Yes, it does work the same way. So here we have 0 and here for some reason we have these different colors. I couldn't see that on record, but now let's see what's with variables. So our variable t is just a single number. So that's probably where the problem is. And it happened. Why it happened? It happened because you don't have minus sign here. So you have lost this minus, and that's probably it. Yes, that's basically it. So you only need to put that minus sign.
The most minor mistakes. Thank you very much.
Not problem. Yes, this can happen to me as well often, so not a problem. Okay, are there any other questions? So if no more questions yet, so then let us continue. Yes, let us continue. And what we are going to do now is to actually send our data represented by my name, surname. Yes, for example, this signal. You can construct similar signal for yourself through this filter and see how it will change. However, there is one thing, because usually we represent these symbols +1 or -1 with some rectangular shape pulses. Now, however, we'll need to make some conversion from these pulses because we cannot send really these pulses in our digital program. Yes, we also need some equivalent replacement for them. So in fact, what we are going to do is to read samples of this signal accordingly, +1 or -1, and these samples are these signal values what we will use. So I will return to this idea in few minutes, but first let us say that this is task 2, for example, and this was task 1 to construct this. So basically, yes, we can say that this is task 1. So using double percentage makes, at least in MATLAB, sections of the code. You can run specific sections separately, yes, if you want, and this also highlights it. In Octave, however, there is no such functionality, but you may use it for convenience in MATLAB if you are using MATLAB, yes. So this was accordingly impulse response, impulse and frequency response plotting. The task 2 is accordingly filtering data in channel model. So this filter is the model of our channel. Yes. Also, what we need to do is to actually multiply this gamma parameter. So where we have this HRC, we need to multiply it here so that maximum value is limited by this gamma. Yes, so usually we had it set to 1, but now we know that it has to lose some of the amplitude because of the path loss, yes, of the channel. Just by traveling some distance, our amplitude decreases. And in my particular case, this is 0.6. In your cases, well, you have different values, but the idea is still the same. Without this gamma, we had 1 maximum value, and well, this corresponds to 0 loss in channel, yes, which is not really happening in real life. So this is the task 2. So what we need to do here is first is specify our signal. Yes, we will specify it as x. So I'm going to maybe a little bit make like this to see and type at the same time. So just by separating with commas, I am specifying this array manually. Yes, as a vector line, a vector row. +1, I have it 4 times. -1, +1, and I repeat this until I get 15 symbols. So if you run out of symbols, like in my case, I had to use my name twice. Yes, if you have extra symbols left, yes, so you stop when there you encounter 15th symbol. So at any rate, the number of symbols must be 15. Or we can check that by running code, and in workspace it should mention that it's 1 by 15 dimensions, right? So everything is correct. Now this is our data we are going to send. Now I want you to show some picture from one Russian language resource, but it doesn't matter, because what matters here the most is the picture itself. Yes, so the idea how we transmit this data is that we make samples from our rectangular pulses right in the middle of this pulse. So basically here we had +1, then we have -1, -1, and so forth. So first of all, we make these pulses right here, and then accordingly apply our filter, and this well makes this signal after filtering. So basically this goes to our RC filter. It's not a resistor capacitor, it is raised cosine. Yes, raised cosine filter. It's not most how to say it, most good name, so I will say that it is raised cosine. Otherwise you might confuse it for electronic components, resistors and capacitors. Yes, so it's not RC in the usual way, raised cosine filter. Okay, so and as a result we get this signal. Yes, of course now you will see that it's simple in theory, but in practice, once you work with digital signals, there are many factors to consider, and I will explain them to you. One more thing, what happens here is the carrier modulation. Yes, that we multiply then this signal with some high frequency carrier and we obtain binary phase shift keying signal, BPSK signal. Yes, but we will not do that today, so that step is missed. What we want to do is these operations, right? So, and we will want to actually show these original pulses as well in this plot. So this is our goal, what we want to finish today. So let's do that step by step. First of all, we have entered our signal. But before that, now we need to actually consider that here this impulse response was like this. Yes, in our case, we have additional samples between 1 and zeros. And these samples need to be considered. Yes, and this is considered by introducing extra zeros between signal samples. So basically, what we want to do is to represent this pulse with, how was it named? Sorry. N SMP values. So basically, we have to have it sampled. So in total, we will have n SMP value. Furthermore, we are going to set all the samples to zeros except for the central one. So basically here, in my particular case, I have an SMP7, and that means that I'm going to have one value set to 1 and 6 others to zeros, like this. Yes, so 3 zeros, 1, 3 zeros, so that this one is right in the center of my samples. So for that, I'm going to need this, how to say it, signal. Yes, so let us calculate it simply. Of course, now, since I am having this number 7, I can simply specify it manually. Yes, but you have different number of these samples per symbol. Yes, so it's better to make it in program style. Yes, so basically signal, or not maybe signal, but let's name it somehow like x xu. Yes, upsampled. So what we are going to do is to no xu is going to be next signal. So basically this is going to be our x0, for example. Yes, it doesn't really matter the name, but I wanted to find some good name. So what we want to do is to set it to zeros. Yes, all the values zeros, and align them in row. So sample and sample zeros. Yes, so once I finish this command, I'm going to get array of zeros, 7 zeros. In your case, you will have 9, 11, 12, 13, or how many zeros you have in NSMP. It will accordingly make this number of zeros. Now we want to make a central one a 1. Yes. So for that matter, considering that all of you have this NSMP as odd number, yes, its division by 2 is going to produce, for example, in this particular case, 5.5, or in this case, 6.5. So we are going to round it up and get accordingly. Here we get 6, 7. That will be exactly in the middle of all these samples. So how do we do that? We do that very simple. We say that do we need... Well, actually, there is one more thing we want to do. We want to actually count how many symbols we have. Length x, yes, because we will need it to divide. Not to divide, but later to display the plots. Yes. Now, here, what we want to do is set the vector element with the number called round and SMP divided by 2 to 1. Yes, so basically this is the index. Well, we might as well actually make it more readable like this. So we first calculate our index by dividing with 2 this NSMP and rounding it. Round performs a rounding operation how it should, yes, by rounding up if it is greater than 0.5 and rounding down if it is below 0.5, yes, fractional part. And here, accordingly, we are going to set the element with this index to 1. So after launching this code, my x0 is accordingly this array. Now what I'm going to do is I'm going to replace each of these elements, this one, this one, this one, with this entire array multiplied by this value. So this is called Kronecker multiplication, and there is a command in MATLAB called cron that accordingly does this. So basically this means that we upsample our upsample input signal. Yes, so basically now we are going to replace this one value with 7 values, 3 zeros, 1, 3 zeros. Yes, and then that one value will be multiplied with the sign of this symbol. So this is called Kronecker multiplication. And for this Kronecker multiplication, we need to specify two two vectors. First vector is the original vector we are going to upsample. So this is our x. And the second vector is the vector we are going to put into each of the elements. Perhaps this works also for entire matrices, two-dimensional arrays as well. In that case, each matrix element will be replaced by this submatrix you specify in the second parameter. So basically that's how it works. In addition, it multiplies each element with according vector. Yes, so basically after this operation, we can actually not put a semicolon. In that case, yes, in that case, you can see that the console will display the result. So here you can see first 7 symbols, then next 7 symbols, and so forth. Each of them is this converted sample. So basically, this is our x. This is our x upsampled. Yes. So now we are going to filter this signal. For filtering, there is built-in function called filter, help filter. But also you need to know that actually how filtering works is it calculates convolution between impulse response and input signal. So for convolution, we can use conv function. Yes. Now, however, there is one practical, not really a problem, but a thing we need to consider when working with signals. So in practice, it will take some time before we get to the first result. And this time for FIR filters with symmetric impulse response is accordingly half of the impulse response length. So we need this delay value. I think I started talking about it in last lecture, but in last, not lecture, but practical exercise lesson, which was an hour ago, but we didn't really get to that point. So now we need this delay to be calculated, yes, and accordingly it's quite simple to do. So basically what we do, we say that delay is going to be half of our impulse response length. Yes, so we need to calculate length of HRC, and then we need to divide it by 2. Yes. And accordingly round it down. But there is another way to actually find. You see, this delay will always point to the maximum value of this impulse response. So instead of making it not really reliable in the sense that later on I'm going to change this filter and it may not be in the middle, right? This maximum may be somewhere here, for example, later on. And in that case, I will have to redo some work. So I'm going to make it right now correctly by pointing out to the maximum. So there is such a function called max in MATLAB, which works obviously by finding a maximum of impulse response, for example, like this, which is set to gamma value. I have done it on purpose, right? Now, however, help max. We look some help, we'll find out that in addition to finding the maximum itself, we can also find the position where this maximum is located. So it works like this. So this will be max val, and this will be max index for maximum of HRC. So now we can see that maximum value is 0.6, and it's located at 36th position, which, as I said, is exactly half plus 1. Yes. So because half will be 35 and plus 1 is exactly 36 of our HRC, yes, which is having the length of 71 symbol. So we are going to use that to find this delay. And in fact, we don't really care for this maximum value, so we may even skip its saving. So in that case, if function returns multiple values and you don't need some of them, you can use this tilde operator and it will accordingly just skip without saving it. In this particular case, we already have this maximum known, which is set to gamma, right? So basically, I'm going to find this delay. Find delay of filter implementation. So we now are talking about how it will work in real life. Yes, in real life, it will have this delay. In fact, I'm going to show you that indeed it is that delay, but let us first calculate it. So now what we are going to do is to filter this signal with our channel. Yes, so now we are going to send signal to channel. And accordingly, we are going to get output signal. Y out, or just simply Y, yes. So this is going to be filter. Now, filter command also uses, how to say it, the transfer function parameters. Yes, so just like frec_uz. Actually, let's maybe see that in internet. Yes, MATLAB frec_uz. So for documentation, the transfer function is usually made in some way of the fraction, yes, of numerator and denominator. Yes, maybe there is a better example even. Yes, like this. In general, yes. So numerator consists of b vector values and denominator according of a vector values, yes. And filter works exactly the same way. It needs to know this transfer function. For our particular case, a is equal to 1, so meaning that we don't have any denominator at all. Yeah. Or you can say that we divide by 1, yes. So that's why we have here 1. And b is accordingly our HRC. Yes. So basically, in that case, we use filter command as follows. Yes. Filter. For b, we set up HRC. For a, we set up 1. And the input signal is XU. So usually this command filter works like filter B A in, right? And this will give us out of the filter. So now we can plot this signal, but in order to have a new window for figures, because currently we have here already many figures, and furthermore these are related to filters, and the next window will be related to the signals. Yes, so we need to make figure windows like this. Here, for example, we are going to have figure 1. Then here we are going to make a figure 2. And accordingly, let us plot our signal y without the x argument, just to see how it looks like. So you can see that actually here we have this delay. That is our end delay. And then we have our signal, yes, represented by, well, our values, right? So let's remind how did they look in my case. So in my case, I had here -1, I had here +1, -1, then +1, +1, +1, and so forth, right? So we need to incorporate this delay. And also what happened is that we are missing some signal values. We didn't quite finish the filtering at all, yes? This operation should continue. So in order to get full signal, not just first part of it, first half of how many it got, yes, we need to actually, during this filtering, append zeros to the end of this signal. So we are going to append some zeros by specifying it in as a new array consisting of our existing array, followed by some zeros. And in particular, we want to append exactly and delay zeros. Yes, so for that reason, we calculated that variable. Well, among other reasons, so that we append zeros to calculate full signal. Okay. So if we calculate it now, you can see that currently we have this signal calculated completely, but we still have this delay. Now we need to cut off this part of the signal. Accordingly, we are going to read our signal starting from n delay +1 value up to the final ending value, right? So here we do trim delay values. So basically remove delay, what we are wanting to do. And now we plot this output signal right here. So currently we can see that indeed we did remove our delay, right? And we now can plot our original signal here just to see if it is received correctly. Yes, and then accordingly we will conclude this practical exercise. So what I'm going to do now is to actually somehow draw my original signal here. Yes, represented by these values. So before I can do that, I need to actually have here correct time vector. Yes, because otherwise it will not really work like that. Also, I think something is a little bit off with this delay. Now I'm going to make it a stem. No, not really stem, but plot consisting of points, just to calculate how many samples I have per symbol. I should have 7 samples per symbol. So now here is 1, 2, 3, 4. No, really, I should have like here 3, then maximum, and here 3 more. So I have 1, and I actually, so let us find out. This should be divided by 7. Does it divide by 7? So 105 divided by 7 should produce us 15 symbols. No, everything is correct, right? So we have 15 symbols. That is, well, actually how it is. Yes, so we now can actually, but then again, shouldn't it be in the middle? Well, we'll see. Let us plot first our signal, then we'll see if it is how it should look like. So I'm going to remove this style of line, and now I need to calculate time values for this signal. Accordingly, we are going to start from 0. So that would be time out, starting from 0, going with the step T sampling, and we have 15 symbols, right? Not 15, but n in general, n symbols, each consuming T symbol time minus T SMP because we start counting from 0, right? So that is our time vector, time output vector. And now we can, let us actually add a grid line as well. And well, maybe labels, X label, so that would be time seconds. Y label, channel signal. So now we can see our signal, but it didn't really reach 15 milliseconds. No, I believe it should. It should reach 15 milliseconds. But then again, it will probably tell that there is incorrect number of dimensions. Let's see. Yes, it doesn't plot like this, so we have to remove this TSMP just to match the vectors of input and output, of time and output signal. Okay. Now I don't like this free space, so I'm going to set limits to this x-axis, yes. So xlim, starting from 0 and ending with n t symbol, just to see it completely. So this is our signal. Now I'm going to plot on top my original signal values, right? And for that reason, I think all I have to do is so xy. Huh. Wait a minute. Xy was appended by zeros, that is correct. Now I need to get rid of those zeros and plot first 105 values without, okay, so I understand. So we can plot multiple plots in the same, how to say it, in the same figure, yes, like this, for example, T out, and here we have XU from 1 to n minus n delay, which we previously introduced n delay zeros. Now we remove those zeros and take only into consideration the signal itself, right? So now you can see this original signal samples as well, how they match, or maybe not exactly really match. Yes, I do believe that here I need to actually make some short shift, starting maybe like this, and here -2. That should be, no, and delay probably -1 like this. Yes, I believe this is the most correct case. But again, as you can see, some of them are a little bit shifted anyway, so it works like that regardless. But this is not really, how to say it, good, because first of all, we need to consider gamma parameter. Yes, as you can see, these orange values weren't multiplied by gamma, so we need to multiply gamma here, because our signal has to be attenuated. Now it matches the point almost perfectly, yes, on this blue line. And the second moment is that actually what I want to have is samples rather than these lines. So basically, I'm going to use not plot, but stem. So I remove this and I will use it like this way. So if I use stem here, and that would be t out, by the way, I didn't remove it, then it will just overwrite my existing plot. So let's see how it works. Yes, I have plotted one plot and then the second one just overwrites and that previous blue line removed. Yes, it's not what I want to happen. So for that reason, I'm going to use additional commands called hold on before the second plot and hold off after it, so that before drawing a new plot, it freezes what has been already drawn and draws on top of it a new one. Yes, like this. Also, I want to make it red color, not orange, so I can specify the color parameter like this, R. Yes. And accordingly, yes, like this. Now, what I would really want to do is to get rid of these zeros, yes, just to see the samples themselves. So for that reason, I need to, how to say it, downsample this time and this signal. So I'm going to do it like this. Yes, I'm going to need downsampled time and downsampled x. So basically t downsampled and x downsampled. So for x, it's quite simple. I'm just going to take this and tell that I take a step of not starting from 1, but starting from 3, and with a step of not really 3, but okay, NSMP here, and here floor NSMP divided by 2. Yes, so this way I start from third value, not floor, but sale, because I need to start from value 4, then next one will be 11, then next one, and so forth and so forth. So basically I just say that start with this value, then goes next this, after 7 values, next this, and so forth. So everything here is going to be skipped. Now I need to do the same thing for this time vector. And it's really the same, yes. So basically I say that the out is going to be like this. I didn't have zeros appended to the out, so I don't do this minus n delay. And here then I replace it with this and with this. So let's see if it looks something is missing. Wait a minute. So xd is 1 by 15 and td is 1 by 4. How did that happen? Wait a minute, something is wrong here. So the out. I didn't specify final value end. Yes, here, missing. The same, how to say it, mistakes when you don't pay attention, yes? So now it's looking just like I wanted. So the final step is to actually plot on top with some dashed line our original rectangular pulses, just to see how did they change. Yes, so basically what I want to do here now is to displayed like this. So yes, so for that reason, I need to add one more plot, and I will be using, how to say it, I will be using stairs function. By the way, here we actually can simplify, yes, by replacing it with our original x. Yes, so basically it didn't change. Yes, so we can use this just like this. So I was going through all this indexing just to show how we will get for time indexes. Yes, but it could work like this either way. Yes. As for time, then for time we really needed to do that. Then I'm going to make one more plot called hold on, stairs, and hold off. Now stairs draws rectangular shaped discrete values. Yes, so basically it simply connects these pulses with this kind of line. Yes. And for that to work, we need to specify correct time intervals. Well, it's quite simple here, yes, because we start from 0, and each pulse has a duration of t symbol. So for that reason, we can say that here we have on time vector starting from 0 and ending with n, which is number of symbols multiplied by symbol time. As for the x-axis or y-axis, we specify our x values, and we need to repeat last one. If we don't, it will not draw complete rectangular pulse. So for example, if you have specified 1 plus 1 plus 1 minus 1 like this, then drawing stairs only for these values will produce the result that looks like this. So basically 1, 1, and minus. That's when it will stop. In order to get this line drawn, we need to actually tell it where it will go. Yes, so that it goes to -1. So for that reason, we have to repeat the final value once again here. So we have some problems. Of course, I know where I'm mistaken. So first of all, we needed to make the range of integer numbers from 0 to n, and then each of these numbers must be multiplied with symbol time, not just the last one. Yes, so we have to multiply every one from 0 to n with the symbol. Instead, without brackets, I would get numbers from 0 to n multiplied by the symbol, which is completely different thing, right? Also, I want to make it red line with dashed style. Yes, like this. So now you can see original pulses, and I don't understand why this line is different color. Let's say that it will be blue. Okay, now it's blue. Yes. So now you can see original pulses and the result. Also, I would slightly change Y limit for this picture because I can't really see well this line. Yes, so for that reason, I'm going to make Y lim as well, starting from -1.5, for example, and ending with +1.5, just to see better this picture. So now you can see clearly rectangular pulse original, then middle value after converting into samples, and then the blue line how this will look like after the passing through our channel. So as you can see, these pulses are no longer rectangular. However, if we just sample these values as we did for the rectangular ones, we will be fine and everything will work correctly. Yes, so that's very important that everything works fine. And one last thing I'd like to show you, what happens is if this phase frequency response is not linear. There is no way I can do this with this filter. I need different filter that will not be symmetric. Yes, so for that reason I am going to actually calculate infinite impulse response filter and then convert it into the FIR. This way I will have nonlinear phase frequency response, and as a result you will see that signal will be distorted. Okay, so let's do this. Yes, I don't know if you had any background on filters and filter prototypes such as Butterworth filter, Chebyshev filter, but I will try my best to explain right now the filter I'm going to use. So I'm going to use what is called Chebyshev type 1 filter. So you can always Google MATLAB help on this function, Chebyshev 1. Yes. And this is infinite impulse response filter. So it has this response with the ripples. Yes. And accordingly, it needs to be calculated somehow. Yes, this help page explains how to use this Chebyshev function. Yes, and as a result of this Chebyshev function, it will generate us vectors of A and B values. Yes, for using, for example, FreqZ, or making transfer function, or making command filter and stuff like that. So basically, we will be able to design our impulse response from this function. So this Chebyshev has multiple parameters. First of them is the number of delay units, right? So in the FIR filter, you had as many delay units as you had number of impulse response samples, right? Here, however, we have loopback, yes, we have feedback, and basically because of that feedback, we don't need that many delay units. So it's quite normal to use like 10, 11, yes, as this number of delay units. And furthermore, exactly for Chebyshev filter, by the way, there is interesting property that it will accordingly specify how many times we will pass this middle line. So for example, here for the orange colored line, I can tell you that n is, let's count how much. Yes, so here we had 1 post point of passing, 2, 3, 4, and 5. So n is 5 in this particular case, yes. So this will determine how many ripples we have. So for 10, we will have 10 oscillations in these ripples. For 2, we'll have only 2 oscillations. But that's not really relevant right now. What's most important is that phase frequency response will no longer be linear. That's exactly what we want to accomplish. Yes, so that this is not a task from the practical exercise anymore. This is just an example I want you to show in relation to our lecture material. So this will not be asked from you to put into a report. So the report ends with these plots. So basically, once you have accomplished that it works like this, yes, you have finished your first practical exercise. Now I'm going to show you what is the difference if this is not linear. Yes, and for that I need to redesign this filter. I'm no longer going to use this HRC filter. I'm going to need some other filter called Chebyshev filter. So I'm going to design this filter by using this notation Chebyshev as it's mentioned in this help, right? Here. Yes, so Chebyshev. First number is the number of so-called order of the filter, yes, of the delay element, of the polynomial degree in denominator, of the oscillations in this plot, yes, and so forth. So I'm going to use, for example, value of 10. It will affect delay, of course, but we'll get to that as well. Next is the level of ripples. So basically, if we return to this plot, the greater value there is, the greater ripples will become. These ripples can go like this, these ripples can go like this, yes. So this is the level in decibels of these ripples. So I'm going to use not quite big ripples because I want still to have as close to linear function in amplitude response as possible. So I'm going to use 0.1 decibel. And the last parameter is cutoff frequency. Yes, so basically cutoff frequency that specifies this transition band's beginning. Yes, so basically where this filter cuts off. In our particular case, I have already closed it, but let me redraw this filter. We have this value specified quite strictly, right, by your parameters. Let's find it out. So this is set to this value. Now we know here that the maximum value is 1 and NSMP is 7. So basically that means that 1 per 7 is your real signal value and other 6 values are zeros. That's in fact what we did here in code by introducing these zeros, yes, putting inside these zeros by using this Kronecker multiplication, upsample input signal by adding 6 zeros per symbol, right? And this will result in narrowing the bandwidth accordingly 7 times. So originally our bandwidth could have been like this. Now because we use this NSMP equal to 7, it will be only 1 of the 7 part. Yes, so basically that means that our frequency should be 1 divided by NSMP for the Chebyshev filter. Let's input it. Let's input it. 1 divided by NSMP. SMP. So what I have obtained are these coefficients of the filter of the numerator and denominator, and now I need to have the impulse response of this filter. As I said earlier, impulse response is obtained by sending the signal consisting of 1, 0, 0, 0, 0, 0, 0, 0, 0, 0 at the input and reading the result. That would be HRC in our case, yes? So we are going to do exactly that by generating signal of some sort X consisting of zeros, and the number of these zeros is going to be, I'm going to uncomment this, yes, the same number as we have here, so length of HRC, except that we want to set the first value to 1. So this way our X will be plotted like this, 1 and then 0, 0, 0, 0, 0. We are going to use this input signal for our filter designed by Chebyshev method, right here. So we calculate the impulse response as the filter operation of BA and X signal. So this is impulse response of Chebyshev filter converted to fear. So at this moment, our infinite impulse response filter becomes finite impulse response filter, because we said that we want to have only length of HRC values of the impulse response. Yes, no more than that. And therefore, it's now finite impulse response. Also, I believe that it will not be originally having maximum value of 1. So I'm going to normalize it. HRC divided by maximum HRC, so that it has 1 at maximum position normalized. And that, I believe, is it, because right now I have this filter with impulse response. Everything further is calculated automatically. So let's see what changes. Okay, something is wrong. It says that I need to load some package in order to use Chebyshev function. It belongs to signal toolbox, yes? So, as I said, it's not a task for your practicals. Still, if you want to, you are welcome to try and do this for yourself. This package is not something that you need to install. I think it automatically is installed. It just needs to be loaded, yes? So it says I have it installed, but not loaded. Once I close Octave, all the loaded packages will be forgotten, and I have to load them again once I open Octave. So I have loaded this package now, and so it will work. I have made a typo mistake somewhere here. Line 24, here, RC. And now we can see the result. Now this impulse response is no longer symmetric clearly, right? This has some oscillations, and phase response is either not really linear. Linear would look like, well, let us maybe have a little bit zoom here. A linear function would have gone like a straight line, but this is no longer a straight line. Yes, it has some, how to say it? Well, non-linearity. Yes, it's a convex line. So for that reason, the phase frequency response is no longer a linear function, and accordingly, group delay time is not a constant. So how did this mess up our signal? You can see it clearly here that in fact our signal has been how to say it, distorted. Yes, distorted to some extent. It still looks quite good, surprisingly quite good. Yes, but still there are cases when we do not really hit our points. Yes, you can see that sometimes we do hit blue line, but still the most of the cases we do not. However, in our particular case, nothing really horrible happened here because, well, as you can see, for the most parts, it even would be greater. So if we would convert our signal, we would still get it correctly. So maybe I need to change some filter parameters to make more non-linearity. Yes, so let's maybe change this order to 15 and see how it will go. Yes, now we clearly see the problem. Yes, so non-linearity also is more obvious here. Yes, if previously I needed to draw a line very specifically, then here you can already see that it's actually not a linear function. Yes, and for that reason, well, maybe like this. Let's see. Yes, it's non-linear, right? Because linear function would look like this. And it's clearly not linear here. And that also led to more distortion. Now that I have more nonlinear function, I have more distortion. And in fact, in this particular case, if I would read this signal, I might have higher risk to interpret it incorrectly and get a negative result here. So that would be error because of this distortion. Although the signal itself is quite strong, yes, it still reads in incorrect positions. That is one problem. The second problem is that actually the delay is no longer so easy to calculate, right? So it's really a little bit variable thing. So yes, this can lead to some very serious distortions. Here also we would read smaller value than actually should be read, yes, if we would read signal here. But still maybe not much examples to show how this problem is happening, yes. But anyway, I hope that you now can see clearly the difference between this scenario when our almost none of these red points actually hit the blue line and the correct channel filter, because both of these channel filters are having the same bandwidth. Yes. But clearly this filter is less suited for communication task than our original filter. So basically I am going to comment this line and everything will return to that filter. Yes, so now I have this original filter, and as you can see, wait a minute, something has, I see. I didn't multiply gamma there, by the way, so I need to do it here, like this. By the way, that means that the previous picture was also incorrect. So let's see how it looks like now. Yes, now it looks even worse. Yes, because of that. Because here we have actually almost hit zero. Here we have also come very close to zero, and basically all the points are smaller than they could be, except maybe here we were lucky. Here we were extremely lucky because, well, we are stronger. Here also. But this has happened actually, you know why? Because inter-symbol interference actually is effect when previous symbols affect current symbols. Here, however, as you can see, we had 4 symbols of 1 in row. Still, this was not enough to save this symbol, so it doesn't automatically mean that everything is fine. Yes, it's quite complex situation. How many symbols are affecting, how they are affecting, this clearly depends on the channel. Yes, so basically we'll talk more about this inter-symbol interference and how to solve it, because sadly, real channels never have this filter response what we designed for our receiver. So basically, once again, I would return to this, our filter. Yes, this is design of our filters we use in communication devices, receivers and transmitter. However, real channels have completely different impulse response, and sadly, they are nowhere near as to what we want to do. For that reason, we have to design a compensating filter in receiver that would accordingly reduce the effect of a channel. But that will be the discussion for the next time. And for today, I have told you everything I wanted. So hopefully you have now a much better understanding of what we are covering in this course. So are there any questions? So
I don't have a question from my side.
Yes. So I see, yes, a lot of material has been given today, and probably you need some time to reproduce results, to maybe change some parameters, but in time over the course, it will become more clear to you, yes, more clear. And well, if you will have any questions later, you are welcome to write them to my email, and I will be glad to help you as best as I can. So thank you for coming today, and see you next week.
Thank you. Have a nice day.
Thank you.
Bye-bye.
Goodbye.
Thank you, bro. Goodbye.